define division as A divided by B equals C if and only if C was a unique whole number. So C had to be a whole number. So what happens if we relax that restriction? We get the rationals. And so our rational numbers we write with this double Q. And so to show you how I'd write it, I would draw a circle with a vertical line and a Q bar. And so that's how I would write rationals. And these are our fractions. And terminating, and I'll tell you why we care about this in a little bit, and repeating decimals. So why do we care about fractions? So just like negative numbers, there's a reason why we would want to be able to find the result of a division problem even if it isn't a whole. So thinking about the solution to 2x equals 3 is 3 halves. That's maybe a really artificial example, but suppose you're making, for 2 batches, here's an example, for 2 batches of cookies, you need 3 cups of chocolate chips. How many cups of chocolate chips go into each batch? And the answer is 1.5. You get 1.5 cups per batch for a total of 3 in the 2 batches. Same for portions, parts, and wholes. So Joe receives half of Mary's salary each month for alimony. And so that's a half of a whole. A ratio, so Republicans to Democrats on a Senate committee is 3 to 5. Or probability, when you toss a fair coin, the probability of getting heads is a half. So there are real reasons why we would care about fractional parts and ratios and things like that. And so to define the numbers of the rationals, unlike our plus and minus, our positive and negative integers, where we can write a pattern, dot, 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 -4, -3, -2, -1, 0, 1, 2, 3, 4, dot, 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 right? We can list them. We can't really feasibly list all of our rational numbers. So we have to use set builder notation. So remember, that's what we call, where we have this, where we have the rationals. So I'll write this. We have the rationals, or the rational numbers, are the set of all numbers written as A over B with A and B whole numbers, and our B can't be equal to 0. So our rational numbers are any number that can be written as a whole number divided by a whole number. And whenever we write it of the form of whole number by whole number, A, that numerator, and B is that denominator. I mean, a little trick they teach kids when they're first learning this is the numerator starts with N for north, so like up, and B, the denominator, is downstairs. And so just at first memorizing what those terms are, but really thinking about what they mean. And that's what we're going to look at next. So to understand the meaning of any fraction, A over B, so A and B whole numbers, B not 0, using the parts to whole model, we have to consider 3 different things. So the whole in question. So suppose this bar here, from about the D and consider to a little past the 0. This is our whole. And then that number B, the denominator, tells us how many equal sized parts that whole has been split into. So if I have my whole hasn't changed, and if my B is 4, that means I have 4 equal parts. And then the last thing we need is we need to know the number, which is A, parts of the whole that are counted or selected or occupied, something like that. So we have our whole, we said our b was 4, and suppose now our fraction is 3/4. Well, the 4 told us how many pieces, and the 3 tells us that we have 1, 2, 3 shaded. And so this represents 3/4, because 3 equal-sized pieces of the 4 possible in one whole are shaded. 3 out of 4. And so we have some models. So I've already used the area model, and I'll say that's probably the most common when you're talking about fractions, kind of more generally speaking. If you're talking particularly about fraction, addition, subtraction, or multiplication, maybe even division, you might use number line. And then set model we really use just for objects. So if you're talking about, like, I have 5 I have 5 textbooks. 3 of them have my name written on the front. How many don't have my name written on the front, right? Or I have 5 textbooks and I put book covers on 3 of them. How many don't have book covers? So that's the subtraction problem. But we have this related notion of how many of mine are covered, and it would be 3/5, because 3 out of my 5 total are covered. So a note about area. So parts of a whole need to be the same size, right? Our definition was how many equal parts. That denominator, our b, was how many equal parts. So here there are 4 equal parts. So and this is a term I would like you to know, 1 over b, which here is 1 over 4, that's called our unit fraction. It's the 1 over however many pieces, so that we have a way of referring to what size we're talking about. So here we have 4 of them, but here we also have 4. And so they need to be the same size, but they need not be the same shape. And so how do we know these are the same size? Well, if we just look at this middle rectangle between the two, because, right, both of them have this square and both of them have this square. But in this one, we're split into 2 this away, and this one we're split into 2 this away. And so because that same piece is split into 2 equal parts, we know they're the same size. I mean, to see that, right, you would just cut 1 in half, move it over, and you can kind of see how you would be able to get those 2 shapes, right? So they need to be the same size, but not the same shape. But often we're going to try to keep them the same shape, because it's going to make our life easier when we're working between different bases, different unit fractions. So here, if we have a whole that's divided into thirds. So here we have a whole divided into thirds, right? That's our unit fraction. And one of them is shaded. We could also go through and split each of these in half, which is what we see here. And when we do that, we see that 2, but not thirds now, but 1, 2, 3, 4, 5, 6, 2/6 are shaded. And instead of then splitting them in 2, if we split them into fourths, so now split each of these in half equally, right? Mine are a little wobbly, but that's why we have this one on the right. We now have 4 of, but not 6 now, 12. 4 out of 12 are shaded. So we have that 1/3, 2/6, and 4/12 are equal because they represent the same area. So fractions are equal if and only if they represent the same area. And so I don't know that I've used this IFF. Let me write that up here. IFF. It's like a super if, and only if. And so fractions can't, if fractions don't cover the same area, they're not equal. So those are equivalent statements. And so we can say that these three fractions, 1/3, 2/6, and 4/12, even though they look different, because they represent the same area, are actually the same number. And so that's another thing we're going to read. These are the same number. And being the same number means if we were to draw the three of these on the number line, they would all fall onto the same spot. They would all fall onto that third. Since each sixth is half as big as a third, when we get two jumps, we're going to fall on a third. Or a twelfth is a quarter the size, and so after we take 4 jumps, we get there. And so we can start to see this kind of coinciding equivalence if instead of using these kind of more general area models like we have here, and we use fraction bars. And so these are called fraction bars. Fraction bars. And lots of books use them, and there are lots of online ones. You'll actually see them in the activity for today. On Tuesday, we're going to be looking at fraction bars and how we can use those to kind of represent some fractions. But if it's only in a little bit today, by tomorrow's our class on addition and subtraction of fractions, we'll use them really heavily. So it's right getting familiar and then starting to use it. Because even in a summer course, I need to give you time to get familiar with concepts before we jump into using them. But when we stack them all up this way, we see those relationships that we had marked up on the previous slide. Namely, I guess not all of them, but namely this fact that 1/6 is 2/12. And we can see that because 1/6 and 2/12 represent the same area. Just like if I switch to a different color, 1/2 is the same as 3/6 or 6/12. Or if we look at the whole 1/1 or 1 whole is the same as 2/2 or 6/6 or 12/12, right? And so there are lots of ways we can get to them. So the fundamental law of fractions essentially tells us that if we take a fraction, 3/6, and we multiply the top and the bottom by 2. Because what's 2/2? 2/2 is 1. So 3/6 times 1, does that change it? No, because 1 was our multiplicative identity, thinking back to yesterday's lecture. So we have 3/6 times 1, which 1 is the same as 2/2, because we drew that here. So we have 3/6 times 2/2. Why am I calling them tooths? 2/2. 3/6 times 2/2 gives us 2 times 3 is 6. 6 times 2 is 12. 6/12, which thankfully is precisely what we had down here. So we can kind of motivate why the fundamental law of fractions, which is, so A over B equals AC over BC, right? So as long as we multiply by that same thing, we don't change the value. You can't see that below my head. Let me see if I can. Ooh, we're going for a walk. So now right above me, we have, it's like the Brady Bunch. AB equals AB or times C over C, which is AC over BC. The nice thing about inequality is means we can go both directions. So if I pick another color, we could both multiply top and bottom by the same thing, or if we have the same thing on the top and bottom, we can essentially cancel them out. So let me pick a color that will actually show up. And so that's the process of common denominators and reducing fractions. So we'll use this for common denominators and reducing fractions. And actually, instead of reducing, because reducing is somewhat, what does reducing make you think of? It makes you think of something getting smaller, right? And when we reduce a fraction, or rather, simplify is what we'll use now. Whenever we simplify a fraction, we don't change its value. We're just giving it a different name. So picture it as like Like if I have a name tag on that says Dr. Dubs, and then I put one on that says Christopher, or I put a different name tag on. I'm still me, I just have a different name tag. And so I think this is one way we can think about a half, 3/6, and 6/12 are all different like name tags that same half fraction can wear. And it would still be an honest representation. So that's actually who they are. So it's like Chris and Christopher, and there aren't longer versions or shorter versions, but right, this is this notion of we could use different names for the same quantity or same area. And so whenever we can't take anything out, so like if we have 3/6 here, we could write that as 1/2 times 3 times 3. And then our fundamental law of fractions says that that's the same as a half, in a way canceling these out as a 1. So this, when you can't do that any further, right, because 1 and 2 are coprime, they are greatest common divisor, the GCD of 1 and 2 is 1, which, right, will always be the case if one of them is 1. And so our simplest form need not always reduce to a unit fraction, but simplifying fractions simplify until GCD is 1. And that's how you know you're done simplifying.